Hi, I'm Thomas Haas, Buick Service Development Manager for the Cincinnati Zone. The know-how program you're about to watch features the 1995 Riviera. If you haven't already seen it, believe me, you're about to see a truly remarkable automobile. Typically, when a new model is being developed, considerable compromise must be made among vehicle stylists, designers, product engineers, and manufacturing engineers. In the case of the new Riviera, there really were no losers. The Riviera is the product of extensive planning and outstanding teamwork between Buick Motor Division and Cadillac Luxury Car Engineering and Manufacturing Division. Now we must extend the teamwork that went into developing the car into the dealership. Customers who buy this Riviera must be made to feel so happy with the car and their total dealer experience that they will want to remain loyal customers for life. I strongly urge all members of your dealership service team to acquaint themselves thoroughly with the many features of this car. The more familiar you become with the car, the more confidence you'll project when dealing with your customers.
There goes Riviera, there goes adventure, there goes adventure in a car. The car is Riviera, adventure is a car called Riviera.
Welcome to Buick Know-How. By now, you've seen the Pulsat program on the 1995 Riviera. That program provides a good overview. But in this Know-How, we're going to hear from some of the engineers behind this great car. And we're going to get down to the nuts and bolts as well. The beautiful skin of the Riviera doesn't reveal the innovative structure of this classic car. Here to tell us more about Riviera's structure is Kevin Davis, body structure engineer from the Cadillac Luxury Car Division.
25 hertz. That was the frequency target we were given. And we had to do a number of things to the body structure which we hadn't done before. We looked at the competition. We also looked at what new kind of things could we do to achieve those kind of targets. One of those examples is here at the base of the windshield pillar. Typically, a windshield pillar will come down the glass and transition into the front body hinge pillar with a very sharp corner at this point. This gives a weakness for transferring loads into the upper structure. So we hid our structure behind the mirror, or what would have been the mirror. Now you see here the transition from the windshield pillar to the front body hinge pillar. We have a much stiffer structure at this location. Another location is where we see a cross-car beam at this point. This provides global structure for the full vehicle. It also provides a support for the steering column, which traditionally is cantilevered from this part of the beam. Now we have an additional structural member inside the IP that supports the steering column and provides that stiffness and that rigidity. And when you drive the vehicle, you'll see that the steering column, as you go over the road or when it's idling, has virtually no shake. Here we see the roof rail. This point here is a single piece stamping from the front body hinge pillar over the roof all the way to the sail. The reason it's a single piece is that we needed to maximize the structure going into the roof. If we consider the vehicle as a beam in bending, we need structure at the top of the beam and also at the bottom of the beam. We needed to maximize this roof section, which meant that the roof outer panel was exposed. In other words, this is a true painted surface, and this can be seen from outside of the vehicle. That gives us the ability to have a good depth of member, and it provides a good structural continuity right the way over the roof. Now, I mentioned the underbody. Also, you need structure in the upper structure, you need structure in the underbody. Here we have a large section rocker, and that is similar to the Europeans, where this is the main load carrying member from front to rear. And you need to maximize that structural member in order to improve that beaming stiffness.
A rigid body structure helps the suspension engineers provide better ride and handling. The springs, shocks, and other components can be tuned specifically to handle road inputs without having to cope with a flexible body structure that acts like a fifth spring. As you saw in the Pulsat broadcast, the Riviera has large doors that feature frameless windows. The door weather stripping system consists of a continuous body-mounted weather strip, secondary seals mounted on the rocker panel, and inner and outer belt strips. The primary weather strip is a rubber seal. Molded joints ensure a tight seal at the belt transition area at the top of the door and at the roof rail to B-pillar. Along the entire roof rail, the primary seal incorporates a captive glass design with a hard winkover. This enables the seal to wrap around the entire edge of the glass. If the weather strip doesn't seal tightly, adjust the glass using the procedure in the Know-How Technician's Manual. If the seal still isn't tight, new weather strip retainer holes can be drilled, and the retainer can be moved approximately 3 millimeters. But there's more to the Riviera's door. The door trim panel is a new design. Before you find out the hard way, let's show you the most important step in removing the trim panel. With the bezels, trim cup, and door handle removed, grasp the panel and lift up and then pull out. Pulling straight out will damage or break the panel clips. The Riviera doesn't have the Christmas tree fasteners you're used to seeing. After pulling up on the trim pad, disconnect the electrical connectors. Carefully peel off the water deflector. The deflector comes off easier with quick, short jerks, a motion that is similar to pulling off a Band-Aid. With the water deflector removed, you'll notice that the hardware and wiring access holes are large, making it possible to remove the glass, window motor, and regulator without removing the complete module. However, when it is necessary to repair several window components, the door window and window regulator are mounted in a one-piece module. This cassette-style assembly provides easy removal and installation. Now, remove the rear lower module bolts and the front lower module bolts. Using a 1/4-inch drill, remove the 8 rivets at the top of the module assembly. When installing the module, replace the rivets with bolts and nuts. The module assembly can now be lifted from the door. Because the body structure of the Riviera is so stiff, the suspension of the car could be designed without compromises. To tell us more about the Riviera suspension, we have Bill Peterson, the Chief Suspension Engineer for the Riviera.
What we did with the McPherson strut suspension, though, we took all the things that we liked and added 6-degree caster. 6-degree caster is essential, we felt, in terms of putting your car directionally strong. What I mean by directionally strong is if you're driving your vehicle down the road and you bend over to tune the radio or you bend over to pick up your cup of coffee, That car has no sense to wander. It wants to go directionally straight, directionally strong down the road. The 6-degree caster gives you that. It also gives you the feeling of a good, responsive, well driver-vehicle relationship as you drive your car through small handling maneuvers. The next component I'd like to discuss is the lower control arm in the front suspension. Essentially what we wanted to do in the lower control arm was split functions. Have one bushing that really was our handling bushing, one bushing that really is the ride bushing. So we took the rear bushing right on center line of axle, made it high in rate so that you got a good, crisp, responsive handling when you had a handling input, a good driver to vehicle one-to-one relationship. Then in the front bushing, we made that the ride bushing. We put it out at an angle where when you did get the vertical inputs, the bushing was very essentially located from a geometry standpoint to be able to isolate well. The bushing is also coned in that when you have just a tar strip type input, the bushing is very soft in rate and isolates that real well. Also, when you have a chuck hole type input, because of its cone shape, the bushing builds up in rate and therefore you don't have crash through. So we completely separated the functions of the two control arm bushings to optimize both ride in the front bushing and handling in the rear bushing.
What you also need to know about these bushings is that the softer front bushing can be replaced using a J41014 bushing removal tool, while the rear bushing is serviced with the control arm and cannot be replaced. The semi-trailing arm rear suspension provides better basic geometry than the more commonly used Chapman strut design. This keeps the tires perpendicular to the road, providing more predictable handling, especially when the throttle is lifted or the brakes are applied in a corner. Bill Peterson is justifiably proud of the Riviera's rear suspension, and he can tell us why it works so well.
The second issue that we wanted to do in the rear suspension of our vehicles was to give the suspension a solid, controlled feeling under a braking maneuver, lift-dive characteristics of the rear suspension. To do that, we had to have a fairly sophisticated shape of our rear control arm to get the geometry that we needed. We did that through a squeeze casting operation in our rear control arm. Squeeze casting is nothing more than a way where we could get this elaborate shape of rear control arm and still get the strength that we had to have to pass durability. Squeeze casting is a method that when the molten metal is cooling, you press high pressure air through the casting itself to reduce all the air bubbles, the cavitation, the resultant porosity of the cast shape of the rear control arm. Porosity is really what controls the overall ultimate strength of the casting. So you can see by the shape of the rear control arm that it's a very sophisticated shape, a shape that if we would have cast it under normal casting methods, we would have never been able to get the durability in the part that we needed. Once we had the elaborate shape, this was incremental in giving us our lift dive control that we need. You can see from the rear suspension that if you just imagined a brake torque coming through the four-wheel disc brake system, we use that brake torque because the front control arm bushing of the rear control arm is so far forward of the center line of rear axle, you actually get a force that we're using under a braking maneuver. Just picture the rear disc turning with momentum and the resulting forces in the clockwise direction. With a braking maneuver, you have a lever arm force pushing down, which is by geometry quite a ways forward of the center of the rear axle. Therefore, that down moment we turn into our advantage by keeping the rear suspension down. We actually have a force at the front control arm to hold the rear suspension down. If you hold the rear suspension down, we don't have any dive characteristics under braking. By having the rear suspension fully isolated, that is certainly what you need in the direction of a soft, quiet, isolated ride. But that is not what you want in terms of handling of the rear suspension. For handling, for optimized handling, you normally want good lateral control, especially when you have a front suspension that is well balanced and well executed from a handling standpoint. You want the rear equally balanced so you have a good knit together feeling car. How we did that is with the lateral link. The lateral link is essentially a lateral stiffness integrity that we give to the rear suspension without compromising the isolation of the ride. The lateral link is nothing more than a handling member. It has nothing to do with the overall ride. It has very little to do with anything else other than making the rear suspension very responsive in a handling maneuver just like our front suspension is.
The rear suspension is world class. To make sure the suspension performs as it was designed, be sure to check and set rear toe after doing any suspension work. To adjust the toe, loosen the inner adjustment link cam nut. Then, rotate the cam bolt using an 8mm wrench or socket until toe is 2/10 of a degree plus or minus 2/10 of a degree. If you have to remove a lateral link, use a J24319-B universal steering linkage puller. Using a pickle fork or driving a wedge between the joint and the link may damage the grease seal. Because of the attention paid to fundamentals such as suspension and steering geometry, Riviera rides comfortably, yet inspires driver confidence even on the most challenging roads. The supercharged 3800 VIN-1 engine is the optional engine for the Riviera, and it will be used in all early production vehicles. In the June timeframe, Riviera will be equipped with a new standard engine, the 3800 Series 2 V6. We introduced you to this new engine in the Pulsat. Although similar in overall appearance to the previous 3800, this engine contains so many upgraded components that it's virtually an all-new design. The Series 2 engine generates only 62.2 decibels of sound at 1,000 RPM, compared to 65.2 decibels for the 1994 3800 tune-port injection engine. Several redesigned external components contribute to this noise reduction. The engine is shielded by an acoustic cover which buffers upper engine noise. A single drive belt drives all engine-mounted accessories. To further reduce noise, the accessories are rigidly mounted to the engine block on newly designed brackets. The large brackets on the old 3800 engine had a tendency to reverberate, amplifying engine accessory drive noise. Down below, there's a new laminated viscoelastic core oil pan. The oil pan is formed from 2 layers of steel, with a sound-deadening plastic compound laminated between the layers. The one-piece oil pan gasket incorporates a baffle. There are other numerous mechanical changes to the engine. For example, the throttle body is larger, and the intake manifold is redesigned. The upper part of the manifold is made of a composite material, while the lower part of the manifold is made of aluminum. Before you can remove the lower manifold, you have to find 2 hidden bolts buried in the right front and left rear corners of the manifold. New cylinder heads incorporate larger intake and exhaust valves with larger ports for improved flow. The new valves have low microfinish valve stems that reduce friction. The camshaft is held in place by a 2-bolt front thrust plate. The camshaft features a larger base circle, a new profile, and a larger bearing surface area. These lighter, stiffer valve train components help extend power output higher into the engine speed range. The Series 2 engine can be safely run up to 6,000 RPM. There are significant changes on the lower end of the engine as well. The deck height of the durable cast iron cylinder block is reduced by 1 inch, making the engine lighter and more compact. The crankshaft is held in place with powder metal caps. The powder metal caps provide tighter tolerances, leading to quieter operation. The first 3 bearings are cross-bolted, resulting in a more rigid lower engine. Conic bearings are used in main bearings 1 and 4. These bearings are thicker at the 45-degree thrust points, where bearing wear occurs most. The pistons have been lightened, and the piston skirt has been refined to prevent rocking. The pistons are tin-plated to prevent piston scuff, and the piston rings are of a low-tension design. The pistons are connected to the connecting rods with floating pins. A new rear block cover helps eliminate engine oil leaks by reducing the number of plugs in the rear of the block. In the event of a leak at the rear main seal, you don't just replace the seal. Instead, The rear main seal and carrier are replaced as a unit. Alignment of the crankshaft and rear cover is critical to prevent oil leakage. The new design also permits the use of a pressure-lubricated rear sleeve bearing for the balance shaft. This bearing is quieter than the roller bearing used previously. The Series 2 engine uses the new 5-digit OBD2 diagnostic trouble codes. When PCM data is selected, a screen appears giving you a choice between PCM data 1 or PCM data 2. PCM data 1 is the same as the PCM data selection on the 1994 Park Avenue with the VIN-L engine, except that the formula for the calculated engine load is different. If PCM data 2 is selected, the first screen shows quad driver operation for injectors 2 and 3 and 1 and 6. The second screen shows quad driver operation for injectors 5 and 4, as well as the operation of the torque converter clutch enable circuit. The Riviera is one of the quietest cars you'll ever drive. While the Riviera is a driver's car, unwanted road and engine noises never reach the passenger compartment. Here to describe the noise isolation systems is Bill Peterson, a vehicle development engineer from the Milford Proving Grounds.
The 1995 Buick Riviera was designed to satisfy our customers' desire for a quiet car. The Buick Riviera's carpet system was designed with 30 millimeters of foam and a ½ pound per square foot barrier to help reduce road noise. To help reduce engine noise, the brake booster was designed with a grommet to help keep engine noise outside of the passenger compartment. Also on the front of the dash, the cable pass-throughs were treated with grommets to again close off the front of the dash and close off the dash mat. The Riviera's headliner was made of a thick absorbing material to help reduce the amount of noise that does enter the passenger compartment. All these designs were put into place to help make the 1995 Riviera one of the quietest cars on the road. The acoustic treatment of the new Riviera was designed in up front, not as an afterthought. For example, for engine noise reduction, this one-piece dash mat was designed with 30 millimeters of foam and a 1 pound per square foot barrier material. This one-piece dash mat provides superior acoustic performance compared to the 7 pieces that were used previously. The one-piece dash mat reduces the number of parts, reduces piece price, investment cost, and assembly time while providing improved acoustic performance.
When servicing the Riviera, don't take shortcuts and throw away the grommets or cutout sections of the noise isolation panels. The grommets and mat were carefully designed to provide superior noise isolation. Riviera uses a new magnetic variable assist steering system. Let me take a minute and explain this in some detail. Magnetic assist steering combines hydraulics, electronics, and magnetics to offer continuously variable effort steering. This system uses a conventional rack and pinion steering gear with an engine-driven hydraulic pump. As with a conventional rack, when the steering wheel is turned, a spool valve opens in the rack, applying hydraulic pressure to assist in moving the rack left or right. Except with magnetic assist steering, a variable bidirectional magnetic rotary actuator has been built into the rack. The rotary actuator has no effect on the hydraulic operation of the rack. The magnetic steering actuator is located above the rack and pinion gear and is integrated in with the spool valve. Using electromagnetic force, the magnetic steering regulates the amount of effort it takes to turn the variable rate torsion bar. The magnetic variable effort steering actuator consists of a coil assembly, a series of magnets, and a pole piece assembly. The pole piece assembly is connected to the valve body. It contains 16 magnet segments that are arranged so that their flux lines connect together. The strength of the magnets varies, depending on the current sent through the coil assembly. There are 16 complementary permanent magnets connected to the spool shaft. From a bird's eye view, these 32 segments look like teeth on a gear. They aren't intermeshed, but they do come into alignment with each other. During low speeds, a negative 1.6 amperes of current is sent through the coil assembly. This energizes the pole piece assembly, and the pole piece magnets repel the permanent magnets in the magnet retainer. The magnetic variable steering actuator acts like an electric motor and assists the driver in turning the spool shaft. At high speeds, the current in the coil becomes positive, energizing the pole piece in the opposite manner. The pole piece magnets are attracted now to the permanent magnets that are connected to the spool shaft, resulting in higher steering effort. The magnetic variable effort steering acts like a brake on the spool shaft. The current sent through the rotary actuator, measured as duty cycle, can be read with a fluke meter connected between cavities 4 and 11 of the diagnostic link connector. To enhance occupant protection in a forward collision, the Riviera has standard driver and front passenger airbags. The airbags are designed to supplement the shoulder and lap safety belts in restraining occupants in the event of a moderate or severe frontal crash. The airbags are located in the steering wheel and the right side instrument panel. The airbags are activated by 2 separate deployment loops. The main function of the deployment loop is to supply current to the driver and passenger side inflator modules. Deployment occurs when the dual-pole arming sensor and at least one of the 3 discriminating sensors are closed simultaneously. The dual-pole arming sensor is located under the steering column support bracket. The forward discriminating sensor is located on a support rail in front of the radiator, and the mid-rail discriminating sensors are located on each side of the chassis. Using a Tech 1, the supplemental restraint system diagnostic codes can be accessed. If a diagnostic trouble code is not current or the ignition has been cycled, the DERM stores the code as the history code, except for a code 51. A code 51 set as the result of a frontal crash must be cleared using the Tech 1. The DERM also contains 2 36-volt resources for emergency deployment. While the supplemental restraint system helps keep passengers safe, the automatic dual climate control system with the rear seat comfort temp helps keep passengers comfortable. By now, you're familiar with dual zone systems, but the air delivery system in the Riviera is different. The valve actuators are electric motors. There aren't any vacuum actuators in the Riviera. Like the 94 Park Avenue, the Riviera has a cold weather cold engine fan delay. This delay prevents the heater system from blowing cold air into the passenger compartment when outside air is cold and the engine is cold. The fan is disabled when engine coolant temperature is below 104 degrees Fahrenheit. The engine has been running for less than 10 minutes. Outside temperature is less than 48 degrees with sun load or 58 degrees without sun load. The fan is in the auto position and any mode other than off or defrost has been selected. Perhaps the most noticeable electrical feature when you first look under the 1995 Riviera hood is the fact that there's no battery in the engine compartment. To gain access to the battery compartment, remove the rear seat cushion by pushing the cushion toward the rear. Then lift the front of the cushion up, releasing the front hooks. Continue lifting up and rotating the seat outward until the tabs that interlock with the seat back release. The battery is a large, heavy-duty 970 cold cranking amp Delco Freedom battery. For jumper cable convenience, a positive battery terminal connector is located in the engine compartment by the washer fluid reservoir. These are just a few of the mechanical highlights of the 1995 Riviera. For additional information, see the Know-How Technician's Manual and the Know-How Service Advisor's Manual. The Riviera was created in response to our customers' desires for an automobile with well-rounded performance and a smooth, comfortable ride. By understanding the car's features, we can best respond to our customers' expectations for what a well-balanced and modern classic should be.